So this is called the mean value theorem, and apparently it's a very important theorem for what a lot of the calculus, when you get to antiderivatives and a lot of calculus is based on. So it says if f of x is continuous at every point of the closed interval a, b, closed meaning it includes the endpoints, and differentiable at every point on its interior, meaning you can take the derivative everywhere inside of those points, then there is at least one point C in AB at which f prime of C, meaning the derivative at C, is equal to the average rate of change, or in other words, where the slope of the tangent line is equal to the slope of the secant line or chord line. Okay, so what that looks like is a picture if I were to graph some function, okay, and let's see if I can do that somewhat okay. So say this is point A and this is point B. And so this would be the point F B comma F of B. And this is the point over here, A comma F of A. A comma F of A over here. And so if I were to draw in the secant line, let's take a different color. Let's take blue. And go like this, let's see. Good enough, right? There has to be some point in this interval at which the slope of the tangent line is equal. So this is the secant line. So what the mean value theorem says is that somewhere in here, there's at least one point. In this case, it appears that there's two places, right? But at which the slope of the tangent line is equal to the slope of the secant line. So if I were to take this line and slide it down somewhere, okay, you see that maybe right at this point, the slope of this tangent line is equal to the slope of that secant line. Yes? You follow that? Maybe also right over here. It looks like there's two places in this case, right? Whoops, I don't want to move my curve. I want to move my line. It's moving the curve instead of moving the line. But you can see that there's probably another place down here where the slope of that secant line is equal to the slope of the tangent line. Why is this important? Well, maybe you're driving down Campus Drive and the policeman said, "You were speeding." And you said, "No, I wasn't. When you stopped me, my speedometer said 25. I said, "Yes, but I timed you going from here to here. And you did this distance in so much time." So I could figure out that your average rate of change, your average speed over that interval was 37 miles an hour. So maybe you were going like 60 at one point, but then you jammed on the brakes on your song. You go, "Oh, I was only yeah, but between here and here, your average speed was this." Therefore, at some point in that interval, you must have been going faster than whatever the speed on 35. You understand? But it's kind of an application of the mean value point. But you could, right? Like if you're going really fast and then really slow, you might be going really slow at one point, but if you're speeding, oh, my average time is or my average speed is this. That's what you're always trying to make up for lost time, you know, when you get stuck in traffic or something like that. So that is a practical application of it. Okay? So then they give you a bunch of problems and they say why the mean value theorem does not apply on the interval. And then they'll say, show that it does apply and why. So the first case we're going to look at is a absolute value function. So if you have like y equals let's do an interesting one, absolute value of x minus 3. And so that looks like, let's see, 3 minus 3 is 4. 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 3 minus 3 is That looks like a V-ish thing, right? V-ish thing, like this, goes up like this, and it goes up like this. And then this would be the point 3, 0. And then is it does the MVT hold on negative, or not negative, let's say 1, 2, 4. Okay? So does it hold on 1 to 4? What that means is there a place between 1 and 4 where the slope of the tangent line is equal to the slope of the secant line? Well, if I plug in 1 in here, what do I get out? Oh, yeah. I plug in 1, don't I get out 2? I get out 2. So there's a point 1, comma 2 up here. And if I plug in 4 in here, I get out, what do I get out? 1, right? I get out 1. And here is the slope of the, so there's the slope of the secant line. Whoops, I should do that in a different color to make it more better. This is a problem that I made up right off the top of my head. And I think it's pretty good because it kind of demonstrates. Does it appear that there is a place within that interval where the slope of the secant line is equal to the slope of the tangent line?
Yeah.
No. And why not? I mean, what rule of the mean value theorem does it violate? If you go back there, if you go back to it, what rule?
It's not differentiable.
Very good. Okay, it's continuous. Is it continuous at every point in the interval? Yes. Is it differentiable at every point between A and B? No. Okay, so that's the problem. Is because there's a corner there in the graph, right? This corner is, the function is not differentiable because the slope changes abruptly from going downhill to going uphill. And you say no, not differentiable. Okay? Not differentiable at 3, 0. Right? And so therefore the mean value theorem does not hold. And you can see graphically that there's no place in here where the slope. What if I said between -3 and 5? Then would there be a place where the slope of the secant line is equal to the slope of the tangent line? Yes, okay, because it would just be the same as the slope of the line. See the slope of the, so from 3 to 5, the slope of the secant line would just be the slope of this line, which is 1, right? And the slope of the tangent line would be exactly the same at all points in that interval. Okay? So that's a case in which it would apply. How about, then we have a piecewise function. How about, does MVT hold for, does hold for f of x equals this thing? You love the piecewise functions, don't you? I like piecewise functions. They're kind of interesting. For x is less than 1 and x is greater than or equal to 1, for the interval, and they'll always give you an interval for this, for the interval from -1 to, let's say 1, okay? Does it hold? What is the value of this function at, 1? If I plug in 1 in here, what do I get out? What do I get out if I plug in 1 in here?
Well,
4.
It doesn't matter.
Okay? Why doesn't it matter?
Oh, wait, that does. No.
Well, if I plug in 1 in here, I get out 4, and this is a cubic function. X cubed plus 3 kind of goes up like this. and then right at 1, I have an open circle. So here is the point 1, comma 4, right? Open circle because it says like x is less than 1. Then as I get to x squared plus 1, what do I get if I plug in 1 into this function? 2, okay? And this looks like the function x squared plus 1, which is a parabola. So we're coming down here, and probably it's going up from there, right? Because x squared plus 1 kind of goes like this, okay? So this piecewise function looks like this. Does the mean value theorem hold on the interval -1 to 1? If this is a point 1, this is a point 1, 2. What do I have here, right here at 1? It's discontinuous at that endpoint, right? And if I go back and I look at my definition of the mean value theorem, or if f of x is continuous at every point of the closed interval, is it continuous at b?
No.
No, it's not continuous at b. Therefore, the mean value theorem doesn't hold. Therefore, there is no guarantee. There is no guarantee that the slope of the tangent line is equal to the slope of the secant line. Even though it might be, there might be a place where the slope of the tangent line is equal to the slope of the secant line, but there's no guarantee by the mean value theorem. Okay, so that's kind of what it said. So now we'll do one where it does apply. All right? So let's change color. For f of x, I thought it was pretty cool the way I typed that in there. Didn't you think that was cool, David?
Yeah.
Wait, I have to tell you something. Okay, let's move on. For f of x equals 1 minus x squared, show that the MVT holds and finds holds on the interval -1 to 1, and it's not always going to be -1 to 1. It just happens that that's what they use in this case, and finds the tangent line that is parallel. Do you know this is parallel to the secant line such that, I'm moving over here, f prime of c is equal to f of b minus f of a over b minus a. B minus a. So the first thing that I gotta make sure of is show that this thing is continuous. Okay? So if I plug in 1 in here, do I get out a value? So what's f of 1? 0. And I'm going to plug in my other endpoint, f of -1. What do I get out? 0. Okay? And so the domain of this function, I could find that by going 1 minus x squared. It's got to be what? Domain. I want to find the domain of this function, first of all, to make sure that it's continuous. Okay? So 1 minus x squared has got to be greater than or equal to 0, which means that -x squared has got to be greater than or equal to -1, which I flip the inequality when I divide or multiply by a negative. Less than or equal to 1, which means that x is either less than or equal to 1 or greater than or equal to what? -1. Okay? So if I plug any values in here for between those 2 points, I think this function is always going to be defined. Would it not? Would it not? If I plugged in like, what's a point between -1 and 1? What's an easy point? 0, okay? Is it defined in there, 1 minus 0? What's 1 minus 0? 1, so that's the square root of 1. Actually, and if I graph this, okay, function, all this is the top half of a circle. Because if I have x squared, remember x squared plus y squared equals the radius squared? And if I solve this for y, I get y equals 1 minus the, 1 plus or minus the square root of 1 minus x squared. And they're just taking the top half of that. So what this actually looks like is a semicircle, okay? Where this is the point 0, comma 1 up here. Am I in the way? 0, comma 1? All right. So it's defined. It's defined and continuous. Defined and continuous. So the first part of the mean value theorem holds. And then I have to make sure that it's differentiable at every point in the interval. So I have to take the derivative of this, which David is going to do for us. Okay? What's f prime of x? Do you think you could do that? I need a different color. I don't like this one. I like purple. Okay. Let's do f prime of x. You want to give that a shot, David?
Would it be 2x times 1/2?
Negative 2x. Negative 2x times 1/2, because you have to write negative x squared
Yep.
times 1/2 times the square root of 1 minus x squared raised to the what? Negative 1/2, which can be rewritten as negative x over the square root of 1 minus x squared. Where is this undefined? At x equals plus or minus 1. But that's okay, because the function itself is defined there. But if we go back again, okay? I'm just going back to here. F of x is continuous at every point of the closed interval, which it is, and differentiable at every point on its interior. That means between those points, between negative 1 and 1. So is this function going forward, okay? Is this function differentiable at every point between negative 1 and 1? Yes, okay? And so, yes, okay? So the mean value theorem holds because it's differentiable. It's undefined at plus 1 and minus 1, but that's okay because it just has to be differentiable between those 2 points, even though it's not differentiable here and here. And it's not differentiable because the derivative is infinite at those points, right? They have a straight up and down slope. So anyway, now I got to find out where f prime of c is equal to f of b minus f of a. So this is the point you could just see from looking at the graph, or if you plugged into this equation, this is the point 1, 0. And this is the point what over here? Negative 1, 0. Okay? So here is my secant line. Let's do it in a different color. Green. Let's make it kind of thick. Okay? Here is my secant line. Okay? What is these? Whoops. What's the slope? So this thing right here, in this case, I don't want that thickness anymore. Okay? So what's f of b minus f of a over b minus a? That's equal to 0. So what I want to see is where is the derivative equal to 0. So all I do is I set this function equal to 0. Where is this function equal to 0? When the top, not when the bottom is equal to 0, that's when I find it where a function is equal to 0 by setting the numerator equal to 0. So at x equals 0, f prime of x is equal to 0. Right? What's y when x is equal to 0? Plug into your original function. What's y? What's y?
Square root of 1.
What is the square root of 1? 1. Okay? So at x equals 0, it says that the derivative is also 0, which means what's true about the slope of the line at 0, comma 1? It's 0. So if I were to draw in the tangent line right here, okay, at 0, ooh, that's really bad. It should have a slope. I'm going to try to nudge it up. All right? Can I do that?
You can rotate it.
Oh, I can rotate it? Sorry, there's probably a better way. Yeah. Uh-oh. Can I just drag it? There. Okay? So this is the line whose slope is the same as the slope of the secant line. And it just happens to be 0. What is the equation of this line if it goes through the point 0, 1? What's the equation of that line? What's the equation of a line that goes through 0, 1 and has a slope of 0? So the equation of that line is y equals 1. So this is the answer to the problem. Show that, and what it should have says find the tangent line that is parallel to the secant line, which is what I just did. Y equals 1. Yes. Questions? Great.
When you found the domain.
Okay. So sometimes this is really a rough sketch, but they'll say find the. So here's the equation of some function. I'm just doing a real simple one so we could kind of get through it. Find the point C such that f prime of C is equal to f of B minus f of A over B minus A. And the way you do that is by first taking the derivative, 3x squared plus 2. And so here's the derivative. And then you want to find f of negative 1, right? F of negative 1, if I plug it in here, is negative 1 minus 2 plus 1, which gives you what? Negative 3 minus 2, right? And f of 3 is equal to 27, 27 plus 6 plus 1, which is big number. What's that, 34? 34. And so the slope of the secant line is going to be 34 minus 2 divided by 3 minus negative 1, which is 36. Oh, look, it comes out nice. I made this one up. 36 over 4, which is just 9, right? So that's the slope of the secant line. And so what you want to do is figure out where the derivative is equal to 9. Yeah, so what you do is you set up 3x squared plus 2 equals 9, and you get, 3x squared, it'll work, equals, it doesn't work,
Plus or minus.
equals 7. Oh, it works. X squared equals 7/3. Okay? So x equals plus or minus the square root of 7 over the square root of 3, or the square root of 7/3. Negative would throw me outside of my interval, right? So you would take the top one. So x would be, which is equal to c, would be square root of 7 over 3. So that's the point at which the slope of the tangent line is equal to 9. Okay? And then you can plug x back in and find the y coordinate. Yeah. Okay? Which I'm not going to do because it looks gross. But that would be more of a place where it's not 0. Okay? Lastly, I just got to talk about a couple things. One more thing. If f prime of x is greater than 0 on AB, on a open interval. Let me just look at my notes a second. Am I still recording? I'm still recording. On AB, then f is increasing there. Increasing if f on that interval, f prime x is less than 0 on AB, then f is decreasing. So this is kind of it comes out of the mean value theorem. Where it comes out of, I'm not going to go into. But, so they will give you a problem like this. Determine, and you probably remember this from pre-calc just by looking at the graph, but now we can determine where f of x equals x cubed minus 2x plus 1 is increasing, and decreasing. Could you do that? Not without a calculator. Okay, this would be non-calculator. So what you have to do is first find the derivative. So I'm going to go f prime of x is equal to 3x squared minus 2x. And the first thing I'm going to do, minus 2, thank you, minus 2. And I'm going to see where that is bigger than 0. So you have to know how to solve an inequality. It's not that hard. 3x squared is greater than 2. 3x squared is greater than 2, which means x squared is greater than 2/3. X squared is greater than 2/3. Or x is greater than 2/3, square root of 2/3, sorry. X is greater than the square root of 2/3, or x is less than the negative square root of 2/3. So that's where this function is increasing. So whatever that function looks like, I know that if this is the square root of negative 2/3, and this is positive square root of 2/3, my function is going uphill here, and then it's also going uphill here, which means it might be doing something like this, okay? Okay, which means it's probably decreasing in here, okay? And the way you would do that, to find out where it's decreasing, f prime of x is less than 0, and you would indeed find that it's decreasing from here to here, which is a cubic function, which looks like that, okay? So that's the end. Your homework, I didn't get through everything.